This video covers unbalanced forces, meaning accelerated motion. In our last video, we saw examples where all of our forces were balanced, meaning that our object was either moving at a constant speed or it was at rest. So if it's not doing either one of these, then the forces must be unbalanced. If the forces are unbalanced, then the object will accelerate. So when we say that unbalanced forces, we are saying that one force in particular is overpowering the other forces. So you're causing an acceleration that direction. Again, that doesn't necessarily mean that it's moving in that direction, but that the acceleration is in that direction. Remember that the acceleration of an object is directly proportional to the net force and inversely proportional to the mass. So here we're seeing these symbols that represent proportionalities. So these little fish symbols here. So again, it's telling you that acceleration is proportional to your net force, and acceleration is inversely proportional to mass. Again, when you say inversely proportional, you're saying 1 over. Again, all of this is just telling us about Newton's second law, which is the net force is equal to mass times acceleration. Remember that this is talking about the net force and not just the force in the x or just in the force in the y, but the net force. So when you're doing these types of problems, make sure that you always draw a free body diagram, that you resolve any vectors into components, meaning that if you have a force that's at an angle, make sure that you get the x and the y. Also that you write the equations of motion by adding and subtracting vectors to find the net force, and we'll do an example of that in just a bit. And then solve for any unknowns. So this is a very simple example of an accelerated motion. So here we have a 10 kilogram box being pulled across the table to the right by a rope with an applied force of 50 newtons. Calculate the acceleration of the box if a 12 Newton frictional force acts upon it. So make sure that we always draw a free body diagram. Again, you might think that you already see a free body diagram, but I'm going to go ahead and draw one over here anyway. So all the forces acting on it, we have the force of gravity acting downwards. We have the normal force acting upwards. Here we have a force applied, and this is 50 newtons. And then we have a frictional force. So if it's specifically asking for us to calculate the acceleration of the box, we know that in this particular situation that the normal force and the force of gravity are going to be equal. So it's not going to accelerate in that direction. So I'm going to focus on the sum of the forces in the x direction, because that's where I'm going to have my acceleration. So my force applied is positive because it's going to the right, and my force of friction is negative because it's going to the left. All of this is equal to mass times acceleration. Now, you need to be really careful here. You need to make sure that the mass involved is the mass of the system that we're talking about, and we'll do examples where m is not necessarily the mass of the system. Also, here you always want to make sure that your acceleration is in a positive direction. That doesn't necessarily mean that it's always to the right. So in this case it happens to be, but that will not always be true. So make sure your acceleration is always positive, and that comes with describing a coordinate system. But again, we'll talk about all of this in a little bit. So here I went ahead and put in all of my values. Again, what I'm trying to solve for is acceleration. So I get acceleration by itself, so I need to divide by mass. And then now that I have my equation equal to acceleration, I put all of my numbers in, and I get a value of 3.8. meters per second squared. Now this example is a little bit more typical of the types of problems you're going to see, where you're going to see a combination of both force problems and kinematic equation problems. So it says that the speed of the head of a red-headed woodpecker reaches 3.7 meters per second before impact with the tree. If the mass of the head is 0.06 kilograms and the average force on the head is 6 newtons, find the acceleration of the head and the depth that the woodpecker reaches into the tree. So again, here I can see the amount of information I'm given. I can use it to help me solve for acceleration. So with force and mass, I can solve for acceleration. So again, that's net force is equal to mass times acceleration. Solving for acceleration, I get 6 divided by 0.06, and I get 100 meters per second squared. Okay, now that we have acceleration, then I'm asked to solve for the depth that the woodpecker reaches into the tree. Again, I can see that with the amount of information I have, I can use this to solve for a delta x. So, again, going back to kinematics, I need 3 pieces of information. So I have 1, I have 2, and this 3.7 is my initial velocity. Again, it says that this is happening before impact, meaning that when we come to a stop is when we've reached our maximum depth. So 1, 2, 3 pieces of information, and we're trying to solve for the 4th, delta x. So the only equation that has all 3 pieces is v f squared equals v naught squared plus 2a delta x. So here, my final velocity was 0, so I can go ahead and cross that piece out. Again, we're trying to solve for delta x, so that's negative 2a delta x is equal to v naught squared. Getting delta x by itself, I get v naught squared divided by negative 2a. Now here I have a displacement of negative 0.0, and I'm going to go ahead and round to 7 meters. What that says is that we are displaced to the left of where we started. That means, if you imagine what the situation is, that actually doesn't quite make sense, which means we made a mistake somewhere. So I'm going to go back and notice that I should have had a negative here, which comes from my woodpecker. If I had a woodpecker like this, then I will have an average force acting on the woodpecker from the tree. So this is our force applied. So I really should have had a negative 6 here. And if I had a negative 6, then this becomes a positive 0.07 meters, which gives me a positive displacement, which makes sense. Again, right now that didn't really affect your numbers, but when you start doing free body diagrams, it's going to be really important that you always draw one, and since we didn't draw one, then we missed our mistake. So last year, we talked about Newton's third law. For every action, there's an equal and opposite reaction, but we didn't quite use it to solve any problems. This year, we're actually going to use it to solve a lot of problems, or it's going to make some problems a little bit easier, and we'll see an example of that in a bit. Here, the force of the nail on the hammer is the same as the force of the hammer on the nail, and the same thing that if you are pulling on something, you cannot pull any harder than it can pull on you. Also, just to clear up a misconception, if you have an object sitting on a desk and you have the force of gravity written on it, and you have a normal force being applied, these two forces are not action-reaction force pairs. The force pair for mass times gravity, which is this one down here, would be the force of this box pulling on the earth. That would be the action-reaction pair. And for our normal force, the action-reaction pair would actually be the force that the box is applying to our table. So when you're drawing free body diagrams, you don't show action-reaction pairs on one object. You need to show that there's two objects and one force is acting on one object and the same force is acting on a separate object. And we'll do an example of that in a bit. So we're going to see that Newton's third law come into play a little bit more here. It says an astronaut constructing a space station pushes on a box of mass m1 with force Fa. The box is in direct contact with a second box of mass m2. What is the acceleration of the boxes? And what is the magnitude of the force each box exerts on the other? So, always starting with, and here I'm just going to go back and draw a picture of what I think the situation is telling me. So I have my astronaut, and it's pushing on a box of mass 1. This box is in direct contact with another box, m2. Okay. So, I'm going to draw a free body diagram for my first object, which is mass 1. So on mass 1, I have a force being applied, and the force of mass 2 also acting on it. So this is mass 2 acting on 1. If I were to draw a free body diagram, for the second object, the only thing in contact or the only thing applying a force is the force of object 1 on object 2. From here, I can see that only two forces are acting on my first object, but one force is acting on my second object. Because they are in contact with each other, they're going to have the same acceleration. But I also know from Newton's third law that F12 is equal in magnitude, but opposite in direction to F21. And that's going to help us solve this problem a little bit later. So if I write the sum of the forces in the x direction for both of these objects, I write the force applied minus F21 is equal to mass 1 times acceleration. Again, I'm only using mass 1 here because that's what I'm describing. All the forces on only mass 1. For the second object, the sum of the forces in the x direction, I have F12, which is positive because it's going to the right, is equal to mass 2 times acceleration. So again, if I want to solve for my acceleration, I want to make sure it's in terms of things that I already know. In this case, all that I know is that mass 2, mass 1, and the force applied. So my acceleration needs to only have those three variables because I don't know what F12 or F21 actually is. So I'm going to use the fact that this piece, M2 times A, is equal to F12, is the same as this piece right here. Again, going back to Newton's third law. So I'm going to make that substitution. Anytime you have two equations with two unknowns, I can substitute. So this is force applied minus, I'm going to go ahead and put M2A is equal to M1A. Now I know all of these values. I want to get A by itself. So I'm going to combine the A's. And then now that they're together, I can factor one of the A's out, or both A's. Last step, get A completely by itself. So my force applied divided by mass 1 plus mass 2 is equal to my acceleration. And that makes sense that my force being applied is being divided equally across these two masses to produce an acceleration. The last part is I want to know what the magnitude, and remember it's just numerical value, the magnitude of the force each box exerts on the other. So again, I want it in terms of things I already know. So I can go back to my first equation and say that force 1, 2, which is equal to force 2, 1, is equal to mass 2 times, and here I'm doing substitution in for my acceleration that I just solved for. Force applied divided by mass 1 plus mass 2. And again, this is the magnitude of the force acting on both objects, again, because Newton's third law. The last part is dealing with system of forces. What this means is if I have a force being applied, let's say we have 3 objects, mass 1, mass 2, and mass 3, all tied together. So I'm going to say that these are ropes in between. And then the third one, I'm going to call it a force applied rather than a tension. It's the same thing, but here I want to make that distinction. That's an A. Okay, so if I wanted to know what my acceleration is, because if I start applying a force, and I want to know what my acceleration is, I can say that this is a system. So when I go to write the sum of the forces in the x direction, well, I only have one force being applied to this system. And that force is equal to the mass of the system, which is mass 1 plus mass 2 plus mass 3, times the acceleration of the system. Again, the acceleration of the system is the acceleration of each individual piece, because if they're tied together and we assume that the string is tight the entire time, then the acceleration is the same for all 3 pieces. So here, my force applied divided by my 3 masses, which is something we saw earlier, is equal to my acceleration. So again, when you have a problem like this, when you have multiple objects being tied together, you can always think of them as a system. Well, now that I know this information, let's say I wanted to go back and solve for the tension in between the individual ropes. Now, this is not going to be the same. So we need to go ahead and draw the free body diagrams for each individual box. So for the first box, we only have one force acting on it, and that's the tension of 2 on 1. So again, remember our notation from last year? The force of 2 on 1. So here I have a lot of... Okay, there you go. So going on to the second object, we have 2 forces acting on it. And I know it's going to be accelerating to the right, so I want to make that one a little bit bigger so we can get to the habit of showing the magnitude of forces on our diagrams. So for this one, I have the force of 3 on 2. And this one's the force of 1 on 2. So I can already start seeing that F21 and, T12 are the same in magnitude. And then when I write the free body diagram for the third one, I have my force applied. My force applied. And my tension of 2 on 3. Goodness. So let's start with the first one. I have T21 is equal to mass 1 times acceleration. Remember that when we are writing the sum of the forces in the x direction, You need to make sure that the forces that are acting on one object, that's the only mass that you consider. So here we're talking about the forces acting on object 1, so we're only considering object 1, or the mass of object 1. We already figured out what our acceleration was, so I can actually just plug all those numbers in. And now we know what the value is for this tension. Now for the second one. I have T32 minus T12 is equal to mass 2 times acceleration. Again, I already know what acceleration is, and actually, by this time, I even know what T12 is. The reason that I know is because T12 is the same as T21, which is what we solved for over here. Now, if I want to solve for T32, I can move T12 over, and I get M2A plus T12. Another way to write that is M2A plus M1A. I can factor out an acceleration. And then substitute in what I solved for acceleration earlier. Which is M1 plus M2 plus M3, M1 plus M2 up on top. And this is 3, 2. Now, I could go back and solve for T2, 3, which is over here. But I know that T3, 2 is the same as T2, 3. They're just equal but opposite in direction.